All right, so good morning, everyone. Today we're going to present the ECG reconstruction project. We really appreciate you taking the time to watch our presentation. So without further ado, let's get started. Next slide, please. So first, I'd like to briefly talk about the motivations and goals of our project. Electrocardiograms, or ECG for short, measures the electrical activity of the heart. A complete set of ECG consists of 12 signals, yet measuring 12 leads of an ECG can be time-consuming and resulting in higher diagnosis rates. And this motivates us to design a machine learning solution to reconstruct the 12 leads ECG with only 2 or 3 leads of input to improve the data collection efficiency and reduce the chance of lead misplacement. Our project therefore aims to evaluate how well machine learning reduces the need for collecting 12 leads of signal, and if it can reduce the need for error-prone chest placement. And more specifically, we aim to develop a deep learning model that only uses signals from 2 or 3 electrodes and can synthesize the rest of the missing leads. Next slide, please. So a quick background about the ECG here. ECG is an essential first-line tool in the diagnosis of many different types of heart conditions. According to the Centers for Disease Control, more than 69 million ECGs are performed annually in the US during doctor's office and emergency department visits. Taking an ECG test requires a health professional to attach 10 electrodes, and these electrodes are used to generate what is called a 12-lead ECG. The accuracy of limb electrode placement does not have much impact on the signal. However, the location of chest electrodes, V1 to V6 on diagrams, are critical. Studies have shown that even trained health professionals can misplace the chest electrodes. And one study found that only 10% of participants, including doctors, nurses, and cardiac technicians, correctly applied all the electrodes. And misplaced chest electrodes can change the expected signal and result in missing certain diagnoses. And this motivates us to seek a technical solution that can reduce the time and complexity of ECG collection and the risk of misdiagnosis. Next slide, please.
Yes, I will introduce about the datasets. To prepare the ECG signals for our training and evaluation, we use 2 public available datasets on the internet. The first dataset is this PDB-XL. It includes over 20,000 ECG signals of very high quality, and it has a variety of diagnostic, form, and rhythm labels. And the signals are sampled all at 500 Hz, and each lasts for 10 seconds. So each signals will have 5,000 data points. We split the train validation and test space using stratified sampling over the joint distribution of all the labels. And the split ratio is 70 by 15 by 15. We'll use the same ratio for the other dataset. So the other dataset we are going to use, okay, next slide, please, is the Code15 dataset. So it's a publicly available subset of a private dataset called Code. It contains much more ECG signals than PDB-XL, but the labels are fewer. It has in total 6 Boolean diagnostic labels. The signals are sampled at 400 Hertz, and the quality is lower. So first, some signals are very short and are padded with zeros. So padding is not very problematic for ECG classification, which is the why the dataset was created for, but it is not very suitable for a reconstruction test. So we remove the zero paddings and clip all the signals to 2,934 samples. And second, some ECG signals contains extreme voltage values, usually appearing at the end of the signal when the leads are detached from the patient's body, which cause large losses or even nans in our models. Some other signals are too noisy to be useful. So we discard these low-quality signals when we're storing the dataset. There are more pre-processing steps in the runtime as follows. So as shown in the next slides, so in the runtime, both the input and the output leads of a signal are passed through a Butterworth filter, allowing only frequencies between 0.5 to 60 Hz. This filter first removes high frequency noises, and second, low frequency baseline vendors. Removing baseline vendors is very important because if we fail to do so, baseline vendors will become the main contributor of our model losses. So after this, we perform the mean normalization. However, we're not going to do standard deviation normalization because if we do so, the amplitude relationship between different leads would be lost, and the trained model turns out to be worse. So here's an example where an original signal on the left gets preprocessed and become the signal on the right picture. So we can see that the removal of baseline render greatly improved the signal quality, despite some minor artifact can still be seen in the sharp drop. And next, yeah.
All right, so before we introduce the machine learning models, it's worth noticing that the first 6 leads of ECG signals, lead 1, 2, 3, AVL, AVR, and AVF have linear relationships. So as long as having the information of 2 out of the 6 leads, we can compute the rest 4 signals with very high accuracy. So instead of training a machine learning model to reconstruct these leads, we decide to compute the remaining leads, giving lead 2 and lead 3. So the machine learning models discussed in the following presentation only serve for the reconstruction of the last 6 leads of ECG, i.e. lead V1 to lead V6. Next slide.
So we implement 5 models in total. The first one is a simple linear regression model, a single linear layer with no activation function. The model learns a linear mapping between the input and output. We chose to implement it first due to several reasons. So it's simple and fast to train and serves as a good baseline. Also, linear regression is interpretable. This helps us identify and verify the linear relationship mentioned in the previous slide. Another natural fit for processing temporal data is the long short-term memory model. So LSTM is capable of learning long-term dependency and patterns in temporal data. And next, we implement a convolutional neural network. The CNN consists of a stack of 1D convolutional layers, each followed by an activation function. Every layer will have an increasing number of output channels, and the number of output channels in the final layer equal to the number of output leads. One thing worth mentioning is the use of seam padding. This is to ensure that the output size matches the input size, so that the length of the reconstructed signal is the same as the input signal. So every Con1D layer extracts local features from the reduced ECG signal, and then utilized by subsequent layers to form high-level features. So as CNN models show good performance, we then tried a more complex and capable CNN-based model, the UNet model. The UNet model consists of an encoder and decoder. The encoder network downsamples the input, while the decoder network upsamples it back, and in our case, reconstruct the missing lead in the process. The architecture is designed to capture both local and global context information. Our implementation of UNet uses 1D convolutional layers instead of traditional 2D convolutional layers for image segmentation tasks. So while UNet is good at capturing local and global context information, not all time instance of the ECG signal is of equal importance. Therefore, as we all know, attention is all you need. So as a next step after UNet, we want to try a transformer-based model. And transformer is a sequence-to-sequence model based on the attention mechanism. Similar to UNet, it also has an encoder and decoder. However, the vanilla transformer didn't perform as well as we expected. It didn't capture the local context information as efficiently as UNet. Therefore, we improved on the model and designed a hybrid model that combines the strengths of both UNet and transformer. The hybrid model, UNetformer, as we call it, wrapped a transformer inside the UNet, as we can see in this illustration. The UNet will encode the input, pass the result to transformer, and then reconstruct based on the output of the transformer. And this hybrid model achieves the best performance among all the models we implemented. Yeah, next slide, please.
Yes, so for all the 5 aforementioned models, we use the same and the most commonly used loss function, i.e. the mean square error, which performs good enough for us. And we have 2 additional metrics for the accuracy of reconstructed signals. So to measure the absolute differences between the reconstructed and original signals, we use the root mean squared error. And to measure the relative differences, we use a Pearson correlation coefficient. Yeah.
So for experimental setup, we first want to find the best input leads. So it's proper to have 2 leads from the first 6 and 1 lead from the back 6, so that the first leads can be perfectly reconstructed using the linear relationship. And after testing the lead combinations, lead 2, 3, and V3 are the best, and we use them as the input for the rest of the experiment. And then we tune the hyperparameters for all models except for linear regression, as it has almost no parameter to tune. We search 120 hyperparameter sets for each model for 16 epochs on the PTB dataset. And we use the Optuna framework to tune our model. So finally, after we obtain the best hyperparameter for each model, we train the models for 32 epochs on PB and 16 epochs on CO15. And this number of epochs are just enough for the model to converge on each dataset. On the right shows an example of how we configure the hyperparameter tuning. So with the aforementioned method, we obtain our model results on 2 metrics for each data set. And we also recorded the G-flops to represent the computational complexity for each model. And as a general review, UNet and UFormer are the 2 top performing models, with UNetFormer outperforming UNet by an average of 0.5%, which is pretty low. But in terms of computational complexity, UNetFormer is 38.9 less than UNet, which makes it more favorable than UNet for same level of reconstruction quality. And before we go deeper about computational complexity, we observed that model performances in PTB is generally better than CO15, which agrees with the fact that PTB is much cleaner than CO15. For linear regression, despite its extreme low computational cost, it drops 39.44% from PTB to CO15 in terms of performance. And LSTM is also very efficient, but it still has some room for improvement that cannot be compensated through hyperparameter tuning. So for UNetFormer, it leads other models by a larger margin in CO15 than PTB, which means that it's more robust to noise than other models. And therefore, we suggest that model with high computational complexity or high expressivity is still very necessary for a decent reconstruction. So for visualization, the blue lines represent the ground truth signal, and the red line represent the reconstructed. In this 6 image for the first 6 leads reconstruction, you can see that lead 2 and lead 3 doesn't have a red line because these are just the input leads. And as we mentioned before, we used the linear relation to reconstruct the first 6. So it ended up having a really perfect reconstruction, which is shown by the red lines almost perfectly matching the blue line, as you cannot see any like blue colors on the like image with the red lines. But for the back 6, so for example, we use a LSTM to show us some example reconstruction for this sample. We can see that there's a certain gap from here and there between the red and the blue, which are the indications of the reconstruction error. So we want to compare the model reconstructions, and then we realize that we can obviously see the reconstruction error, the gap between the red and the blue for the linear regression and the CNN, and for LSTM, UNet, and transformer, the gap is more obvious when the signal is noisy. So here's the reconstruction visualization for PTB-XL, and it's for lead V6 of a sample. And as you can generally see, our models, like all the models presented here, seem to have a similar level of reconstruction. And this is because PTB-XL is generally very clean. But for CO15%, we can immediately see that there's a mismatch for the reconstruction of linear regression to the ground truth. And if you look closely enough, you'll find that the UNetFormer is actually having slightly better reconstruction than LSTM and UNet. Yeah. And there concludes our results for the models. And for next steps, we may want to train with larger data set to further improve the reconstruction accuracy and reduce the loss. And we also want to reconstruct 12 lead signals with only 2 input leads.
So yeah, that's the end of the presentation. Thank you for your time. We also want to thank UTMIST who organized today's event, and OnHand.ai, who is the collaborator of our project and provided research guideline and valuable feedback to our results. So yeah, thank you for watching, and we are open to questions.